Hopefully anyone watching this is a fan of native code. There are multiple reasons that we use native code, but one of the main ones is performance. When we're writing a performant program, i.e. one that we want to be fast, we need to have a working mental model of what fast code actually is. Unfortunately, reality is often not very kind to our mental model of performance. The question then is, how do we keep ourselves aligned with reality? As such, we need a systematic methodology for determining where the slow parts of a computer program are. I find myself explaining how to do this somewhat regularly, so I thought I'd compile it into this talk. As such, if you'd like to know how to profile decode, keep watching. Let's say there's a performance issue in your code. Obviously we want to fix that issue, but how do we go about doing that? We could use some kind of divine guidance, i.e. we just start optimizing things that we think are probably slow. Unfortunately, this doesn't really scale. Hopefully, obvious solution is that we need some kind of systematic approach to finding where the performance issues are. Could jerry-rig some kind of measurement into the program, or we could exfiltrate parts of it and measure those independently, but realistically the thing we need is a profiler. So, what is a profiler? A good profiler should produce a simple report of performance issues within a program. The kind of information produced isn't magical. It won't tell you how to actually change algorithm, but it can massively improve your implementation of a given algorithm with regard to performance. You might need a different tool, but you can profile anything that you can measure. Tracking memory allocations is much easier with a profiler. We know what a profiler is, but when should we actually use one? Well, the obvious case is when the program's running slowly. Unless we have a very simple program, we've optimized it before, there's typically a Pareto principle, informally, when it comes to the speed up, i.e. 20% of the work yields about 80% of the speed up. Not 80% faster, but 80% of the speed you gain. Profiling code on representative input, i.e. realistic input, can actually serve to test the assumptions made by the programmers who are writing that code, which probably won't fix any bugs, but might lead to better allocation of resources. There are basically three types of profilers. We have instrumentation to start with, which is probably the simplest, most obvious way to do profiling, where we just actually modify the code using the compiler to insert measurements. The data from instrumentation is typically very complete, but as we'll see later, quite contextless. The next approach is sampling, where we actually interrupt the process, collect data, and keep going. This is harder to implement and harder to get right usefully, but the overhead is much, much lower. The third approach is to actually use a technique called emulation, where the program is translated into an intermediate representation and then interpreted at runtime. So you can then collect extremely dense data, but it's often data that's slightly synthetic, i.e. your code is running on a model of your processor, not your processor. Let's say we have the charmingly simple add function inside a program somewhere, we want to profile it. The way we can profile it is using the DMD-profile flag. As I've shown in the example on the slide, we can see that DMD translates a function from the form on the left to the form on the right, where it's injected the trace prolog and trace epilog functions, which handle the actual measurements, which are then stored by druntime, and then upon program exit, the trace.log file is either created or has its contents merged with the new data. For that reason, I highly recommend deleting the log file on every run. We've seen what DMD has to offer. Can we do better? Yes. Because it only works on functions that it has instrumented, that means it doesn't work cross-language, it doesn't work very well on things which call into the operating system, etc., etc. The data is only collected at the function level, which means it's quite useless for actually diagnosing why the performance issue happened. I didn't mention it previously, but the keen-eyed observer will also note that the overhead is absolutely catastrophic on the previous example. To avoid that overhead, we need to move to a sampling profiler, but that raises the question of what to sample. An old sampling profiler like gprof would just save the instruction pointer, but the way to actually get good profiling data is to sample the call stack. The information density from call stack sampling is actually so much higher than instruction pointer sampling that just by pausing the program in a debugger, you can actually effectively form a poor man's profiler of your own if for some reason you don't have access to one. Just take a few samples, it's much, much better than nothing. If you absolutely have to use this technique, then it works best on programs that have some kind of discrete notion of progress, so you can actually know when to stop it, i.e. in the slow bit. As hinted previously, the debugger and the profiler sample the call stack in exactly the same way. That means you'll need debug symbols, and you may also need to compile with frame pointers in the binary. This shouldn't technically be an issue, but because of the differing quality of the profiler's unwinding algorithm, it may not actually understand the debug info properly. As I've hinted at previously, the built-in profiler in DMD is not very good. The technique DMD provides for profiling memory allocations, however, is quite good. This is something where, although you can use an external tool like Valgrind's Massive or Heap Track, the tool that DMD provides is integrated with the language, so it actually understands the types of dynamic memory allocations, which is very helpful. Here's a very simple example of what this actually looks like with the use profile GC. As you can see, the Visual Studio Code actually understands, obviously if you have the D plugin, understands the output from this tool, which is very nice. Thank you, WebFreak. This type of functionality is really easy to implement in the compiler, but in this case it's actually extremely useful because memory allocation is very slow. And people usually do too much of it. We previously gave the example of add, which, while simple, is completely unrealistic, i.e. it would have been inlined anyway, and even if it wasn't, we couldn't optimize it. To intuit real code, let's think about class hierarchy with a .eat method. If we take a horse and a chicken, they'll both implement .eat, but they'll take different amounts of time to eat. As such, our profiler should be able to give us as much context as possible so that we're actually able to decipher which one was eaten and why it was eaten. Since it uses object-oriented programming and doesn't spend too much time dwelling in one place, let's just take a simple look at DMD compiling Hello World. This was collected using call stack sampling. Try main is the compiler's entry point, and because of our use of stack sampling, we're able to have this very structured, easily interpreted view of performance. With call stack sampling disabled, we lose almost all context and the data is effectively useless. In particular, the use of the visitor pattern is very hard to interpret in terms of performance without the use of call stack sampling, i.e. we lose the context around the place the visitor was used. So to bring it all together, what do we actually want from any profiler, i.e. our dream profiler, if there's anyone on earth who actually dreams of profilers? To start with, we obviously want call stack sampling. We've shown that that's an absolute requirement. We'd like it to be low overhead so we can use it in as many situations as possible. Source level profiling is also quite important in the sense that you can actually relate a performance issue to what code caused it rather than just where that code is. If the hardware provides some kind of information to us, it'd also be excellent if the profiler can actually show it to us. Cross-platform is listed here, but I'm not really convinced it's actually worth the pain, given that if the code runs on both platforms, it's usually enough to profile it and make it faster on one platform, and then the speed up should go to the other. Having said all that, we can now move to our first kind of proper profiler, which is Perf, which is a front end to the kernel Perf event subsystem, which is how the Linux kernel basically aggregates all of its information that it collects about itself, at least related to performance. For now, we're only interested in using it as a fairly straightforward profiler. Perf has a lot of functionality. For example, as well as being a profiler, it's also a both member of and front-end to a large set of tracing systems. So basically ways to optimize systems rather than code. Brendan Gregg's blog is basically the Bible when it comes to FreeBSD and Linux tracing. Perf is mostly platform agnostic, i.e. The code presented later should just work on a Raspberry Pi as much as it does on this desktop machine. But as you get to the periphery of Perf features, you do notice certain things which, for example, only work on Intel, because Intel have contributed the drivers and AMD haven't. The basic workflow with Perf is very simple. Use perf record to get your data, report to view it, and then annotate if you want to actually look at the source code aside with the instructions, so you can relate a performance problem back to the source code. To use call stack sampling, we just have to use -g when we use perf record. Perf report is very easy to use. Unfortunately, perf annotate, if you understand the code well, it can be easy to use. However, it's very difficult when it comes to wandering around code that isn't yours. As far as I'm aware, there exists no option to only see the source code. You have to look at the assembly as well, because it uses objdump. Having just mentioned perf's slightly dated interface, let's look at some profilers that present graphical interfaces. For those wanting to stay open source, there is a quite good GUI for perf called Hotspot. The best tool available to you, however, is likely the profiler provided by the chip manufacturer. i.e. for AMD it'd be uprof, or for Intel it'd be vtune. For me at least, the reason to use these tools is that the source annotation actually works and is actually designed to be used by humans. Since we have a GUI, we can now actually present information much more fluently than we would have been able to with a text interface. A really important example of that is the flame graph. These allow us to present our call stack data in a way which is much more intuitive than just printing a tree onto the screen. They're a fairly simple idea. Each frame gets a box on this heap, which looks a bit like a flame at the end. The x-axis indicates the frequency in the data we collected, and the y-axis, i.e. the height on the stack, is the depth during the collection. A key thing to remember is that the x-axis is not ordered by time, it's ordered alphabetically, which is so it can merge identical frames. On the slide, you can see a very small example of a flame graph. See, this one seems almost pointless. We've ended up with a rectangle rather than the flame. This is because there isn't much branching in the call stack, which means we don't actually get to extract that much information. If instead we look at a more complicated program, we can see the value of the flame graph. Flame graph generation is now a fairly common feature with profilers. If you'd like to generate one with just perf data specifically, then Brendan Gregg has a tool you can Google for. As promised, a more complicated example. This flame graph is of the compiler compiling something, it doesn't really matter, but the point is that we can see these spikes of flame, where we can see the thin ones aren't particularly problematic, but where the flame is really fat, those are things that we should look at. It's of note that this was with a unoptimized build, which is why it looks so terrible. Profiling is normally a fairly informal affair, but if you would like to make a real decision based off some notion of either profiling or benchmarking, given that this doesn't really apply for that as well, there are some techniques you can use to make sure the data is more consistent between runs. Ever since the demise of Dennard scaling about 15 years ago, power usage is something that's really important to processor companies, which means that they'll basically do any trick in the book to save power. Specifically, the processor is often downclocked or parts of it are turned off, which, depending on the load of the system, can mean that your benchmarking or profiling data can actually vary quite a lot transiently. On laptops in particular, the processor might be downclocked for one run versus another, which can make the memory look less slow depending on the clock speed, i.e. if the clock speed is lower, then the memory stays the same speed, so the processor is not as much faster as it usually is relative to the memory. To minimize any variance, you can be very aggressive. For example, you might want to even disable simultaneous multi-threading if you want it to be particularly violent, but realistically, perfectly fine halfway compromise is to just use something like setting the power management systems to be as lenient as possible. I.e. on Windows, that would be power options in control panel, and then set it to performance. Before moving into advanced profiling, I think it would be useful to actually look at a little bit of how the processor actually goes about running instructions. To begin with that, we need to start with the notion of pipelining. Think about how an instruction is actually run on the processor. We need to get the data for the instruction, decode it into something the processor can run that, and then put the state that we generated back into the processor, so to speak, i.e. into registers. Now that we've established our 4 basic steps to executing an instruction, how do we use them? You could just lay them out one after the other, but the thing you can do instead, i.e. pipelining, is as soon as one stage is free, we can start doing the next instruction almost immediately. Using this design, we're able to decrease our cycles per instruction from 4 to 1. This is a large speed up. However, it isn't possible for all code. If one instruction uses the result of a previous instruction before it's ready, then we get something called a hazard, where we have to stall the processor, introducing something called a bubble, which means we'll have to wait for a certain number of cycles for it to be ready. This design is what's known as a scalar processor. If we can execute more than one instruction per cycle, then we have a superscalar processor. The processor you're currently watching this video on is massively superscalar, i.e. they can execute on average anywhere from 2 to even 6 instructions per cycle. As well as being superscalar, a modern processor also uses something called out-of-order execution, i.e. it can identify independent work at runtime and then execute that work, ideally in parallel using the superscalar backend. To find enough work to actually execute it in parallel, the processor uses something called speculation. The processor is constantly speculating, i.e. guessing the future path of the code. This has been an enormously profitable source of speed up for processor designers. Speculation isn't something that the processor opts into, but rather something that's opted out of for certain instructions. The basic concept of modern out-of-order execution was invented by Robert Tomasulo at IBM in the 1960s. The implementation of these techniques in a modern processor is far too complicated to do justice here, but if you're interested in reading about it, Agner Fogg produces an extremely dense monograph about processor architecture, which is basically the Bible on optimizing code for a modern x86 processor. There's a famous paper called It's the Memory Stupid by Richard Seitz, where he correctly identified and predicted that memory performance would dominate the performance of computers for the coming years. This is still the case today. Processors are much faster than their memory. The techniques mentioned previously are mostly intended as a way to combat this so-called memory wall, i.e. it's not hard to see how something like out-of-order execution allows the processor to continue working while waiting for a load from memory. Computer programs are using more memory than ever. However, the way that they use that memory remains fairly predictable in terms of both spatial locality and temporal locality, i.e. we can predict the patterns that the memory is used in terms of their addresses, and we can also guess that memory that has been used is likely to be used again in the short term. When designing the memory of a computer system, the designer has access to basically a choice between big and small or small and fast. This trade-off leads to multiple layers of memory, i.e. we have a very small but very fast cache, and a kind of medium level, and then we have a large, quite slow cache on top, i.e. the last level cache, and then on top of that we have the RAM, which is extremely slow but very large. A particularly slow memory access might take the equivalent of something like 100 instructions. We can do some serious work in that time, which is why the way that a program accesses memory is one of the most important things you can look for in a profile. Here's a graph of some memory latency data from about 20 odd years of processors. In the low kilobytes of region size, we notice that there's a straight line. The straight line up to the bump, the location of the bump on the x-axis is the size of the level 1 cache. The 12900K is Intel's brand new top-of-the-line CPU. Based on this graph, we can see that the bump is at 64 kilobytes, i.e. that's the size of its L1 cache. From this, we can actually see one of the reasons why the AMD FX8350 wasn't very successful. The caches are quite slow and quite tiny. The Athlon 64 is coming up for about 20 years old now, so we can see that in 20 years, there's been quite a lot of progress at the higher levels of the memory hierarchy, but at the lower levels, latencies haven't actually improved that much. The trends on this graph are why some programs can see somewhat counterintuitive trends in terms of their throughput versus the amount of work they're doing in a given batch. Our miss rate for the cache could only decrease by a few percent, but those few percent that do slip through would end up being extremely expensive, which could make a hot loop much slower. Speculation has been enormously profitable for processor designers. However, it isn't all good. We can actually trick the processor into doing our bidding for us. If we get it to touch memory speculatively, and then that speculation then fails, we might expect it to undo all of the work it did, but it actually doesn't. If the processor touches the caches, we can actually do something called a timing attack, where we measure the timings of accessing that memory very precisely, and then any differences we find can reveal what the processor did during a given speculative execution. The attack is slightly too complicated to reproduce here, but if we do it right, we can actually use this attack, i.e. Spectre variant 1 to be precise, to exfiltrate data from anywhere in the virtual address space, which is why things like JavaScript virtual machines inside your browser were very insecure when these kind of hit the news in 2018. It wasn't quite like Y2K in the sense that these are actually quite hard to exploit, but there was a very large effort to go around the world mitigating systems against Spectre, which succeeded, which is why we haven't had any disasters. Now that we can understand a bit about what they mean, we can talk about performance counters. As your processor goes about running whatever you've given it to run, it keeps track of what it's been up to. I.e., we mentioned memory hierarchies before. One of the main things that performance counters are useful for is working out just how well we utilize that memory hierarchy, i.e., how many L1 hits, how many L1 misses, how many times did we go directly to DRAM, etc. To use these on Linux, Perf is the main way of getting access to them. If you just run perf list, it'll spit out a big list of all the things it can show you. If you want to use one, you just do -e and then the name of the event and then your normal perf command. On Windows, however, things aren't quite as rosy. You'll have to use the profiler that your CPU manufacturer provided, i.e. vtune or uprof. So now, let's think about an example of what we can use these performance counters to track. On the right-hand side is a diagram of the microarchitecture of Intel Ice Lake processor, which is the one before the current generation. At the bottom, where the diagram is widest, we can see what Intel called ports. These are the parts of the CPU that actually do the work, i.e. they do the adds, they do the multiplies, they do the loads and stores, etc, etc. For our purposes, it doesn't matter how, but the CPU will at runtime dispatch work to these ports. Key metric of how efficient code is, or rather how efficiently it uses the processor, is how many of these ports are actually being utilized in a given cycle. To help us keep track of this, the processor keeps track of a count of how many of a given number of ports utilized in a given cycle, i.e. we count there were 2 billion cycles where 2 ports were utilized. This processor has almost 10 ports. If we were only utilizing maybe 1 or 2 or even 0 ports on most cycles, that suggests that we can't pull in data into the processor fast enough. We could try to intuit our way through performance counter data using just annotations next to the source code of a given count, but a much more effective way to do it is to use a graphical approach like you can do with Intel vtune. And here is said graphical approach. vtune implements something called the top-down microarchitecture analysis method, which is a handy way to aggregate all of the performance counter data we collect and actually make sense of it. This data is from a profile of a fairly badly optimized matrix multiplication routine. We can see from the data here that it's very memory bound. So if you note that 65% of the memory accesses are actually missing the cache entirely. So if we look at our port utilization metrics that we mentioned before, you can see that 71% of cycles were doing no work at all. On the right hand side, we can see a feature that apparently only vtune has, to my knowledge at least, these so-called micro pipes, which provide a graphical view into the data without having to really dive deep into the numbers. This is one of a number of features that, as far as I'm aware, only vtune has, or at least only vtune does as well as it does. So if you're on an Intel processor and you're able to use vtune, I highly recommend it. AMD's uprof, which we saw earlier, is suspiciously similar looking to vtune, but doesn't implement anywhere near enough of the features to really compete, although the ones it does fine. One thing we can see just at the bottom of the data listed under average CPU frequency is the average CPU frequency. The fact that Intel vtune keeps track of this is very useful because it means that the things I presented earlier under the reliable data section, we can actually keep track of these without writing our own benchmarking framework, for example, to make sure nothing naughty happens. This is the kind of thing you only really get with the level of tight integration that these profilers have, since that the APIs for tracking this data from the processor are quite flaky. This particular example is C code, although obviously it works fine with D, otherwise I wouldn't be showing it, but this is vtune's source annotation feature. The quality of this feature is like night and day when compared with Perf annotate. This is the level of granularity that we lacked with DMD-profile that we saw right at the beginning, i.e. to really diagnose a performance problem, we need to be able to see exactly how much damage each line caused. In particular, with this example, we can see that the cycles per instruction is very high for the main line in this loop, i.e. the part that actually does any work. That's why it's marked in red on the right hand side. This is the kind of thing that only really a graphical environment can show you, because your eyes can just jump directly to where the problem is. When you look at a profile in vtune, you get this handy little box at the bottom. This will actually plot a graph of the thread utilization of a program during a run that you profiled. This is very useful for noticing just how much parallelism you're wasting. Right at the bottom, there's a graph called system bandwidth. By skimming this, we can infer whether we're really maxing the CPU to its full potential. In fact, skimming along the time axis, we can actually see different stages of this program as it went through, i.e. for the most part, the memory bandwidth is fairly low, but then at the end we see a period where we are in fact using much more than we were previously. Another feature that, as far as I'm aware, only vtune can do is something like this, where we can actually present an approximate histogram of the various latencies within the program. In this example, we can see that most of the accesses, in fact the vast majority, are all under 20 cycles, which is very good. As we look to the right hand side of the histogram, however, we can just see there are a few bumps every 100 cycles or so. These aren't a huge issue, but they're a good indicator, especially if these bumps are a bit taller than this, in your program that you need to focus on optimizing the memory usage patterns. Up till now, I've emphasized sampling profilers as the way to go, but instrumentation can actually work if you do it in a slightly roundabout way. If we have a multi-threaded program, it might be the case that we have code which is very busy, but optimizing it won't actually yield any performance. COS is a relatively new profiler that's designed to actually allow you to establish a level of causality to your measurements. It does this by actually performing performance experiments. That is to say that we can infer the effect on speed of a given line by making the rest of the program slower, i.e. we're not just looking for the lines that really matter, we actually directly find the lines that really matter automatically. To help it establish some notion of causality, we need to be able to inform the profiler while running in its environment when some given batch of work is completed. We do this with an API provided by the profiler. If these conditions fit your code, then COS is worth looking into. However, it is something of an investment to use, so I wouldn't recommend it for a general purpose profiling workload. In my experience, it's also somewhat unstable. I wanted to demonstrate it for this talk, but it doesn't work on my Ubuntu install. The last profiler we're going to take a look at is Tracy. Tracy is a hybrid profiler specifically designed for profiling video games. It's designed to be tightly integrated within a video game, i.e. we link with a library that the profiler provides, and then we mark a region inside the game, which is our main frame loop, and then on every frame it sends data over a socket to a server, which then collects the data. Game development is performance intensive, i.e. performance of a game always matters. This means that Tracy has gained a fairly large number of features over the years, and is gaining new ones fairly quickly. Since it's intended for profiling games, Tracy has quite a few features for profiling in a multi-threaded environment. I can't recommend it as a general purpose tool, but for video games it's very good. We've reached the end of the video, so I guess it's time to move on to the Q&A. I think I'll do some more profiling tutorials for our YouTube channel.